So today we're going to prove Euclid's theorem. This is a very old result, dates back to the around 300 BC when Euclid's Elements was first published, and of course that book has since gone on to be in print throughout the previous millennia up to the present day, and one of the most widely read books in history. The theorem that we're interested in today concerns prime numbers, and it's very easy to state the theorem. Here we see it says there are infinitely many prime numbers. So how would we go about proving a result like that? Well, the prerequisites for the proof are minimal. You will need to know what a prime number is and how divisibility works. Basically that's about it. It's an easy proof. The techniques we're going to use are primarily constructing new prime numbers and looking at the cases that emerge. And as I said, the proof was originally due to Euclid. So let's get started. So it's often said this is a proof by contradiction because we're going to start by assuming the opposite of what we want to prove in the end, but it's not actually a proof by contradiction. It just has the set seems like that because we are starting off with the opposite assumption or the negation of the statement we want to prove. Right, let's get started with the proof then. So I'm going to construct a set, I'll call it S. That set will contain various prime numbers, P1, P2, P3, all the way up to the last prime number in the set, which is PR, say. Now this set, by assumption, has only finitely many prime numbers. It's not an infinite set. We're going to assume that there are only so many prime numbers that we can ever find in the world or in maths, and that we can list them all on some list that comes to an end. Now, there's a few things we can do at this point. One thing is to construct a new number, let's call it n, and we're going to just multiply all of these numbers together, all of these prime numbers that were in this set we began with, P1 times P2 times P3 all the way up to PR. And then we'll construct yet another number Q, the names are not important here, which is just n plus 1. Now Q will be an interesting number to look at because, like any number, it will either have to be prime or it won't be prime, i.e. it will be composite. So let's look at the two cases here. Case 1, where Q is prime. So for Q to be prime, then that would mean that we've discovered a new prime number that wasn't already in the original set S. Q has to be relatively prime to all of those numbers, so all of those P1 through to PR have to be relatively prime to Q, so it must not already be on the list, and therefore we can add it to the list, and that means that our assumption that we had listed all of the prime numbers was false or mistaken. You might think, well, maybe we just missed that one, and we can end the list at that point, but we could repeat the process where we multiply all the numbers, and this time multiply by Q as well, and we would discover, if we then added 1 to that product and defined a new variable with that value, that the same argument could be repeated and we could add it to the list, and the list would keep growing. Case 2, where Q is not prime, in this case Q must have a prime divisor. because if it's a composite, then it will factorise into primes, because every integer has prime factorisation, which is unique up to signs. So don't worry if you don't understand that part, but if it's not prime, then there must be a prime number p, little p, which divides q and it divides n. So that basically can't be that. You can't have a prime number which goes into some number n and it goes into some number n plus 1. There's no n's and p's which satisfy this. There's no integers and prime numbers which satisfy both of these relationships, because that would, in order for it to go into n and n plus 1, it would need to also divide 1, and no prime number divides 1 evenly. So we have, in this case, we have constructed a number p which wasn't in the list. So no matter whether it's case 1 and q itself is prime, or case 2 from q we construct p which was a prime number not on the list, either way we construct a new prime number that's not on the list, and the list grows. So we can't list all of the prime numbers in a finite set, therefore there must be infinitely many prime numbers. So that concludes the proof of Euclid's theorem.